In this video, we are going to solve two related problems. One for the maximum shear stress on a twisted cylinder, and the other for the shear stress within the twisted cylinder, within a particular region. We look here and we see that we have a torque of 85 newtons for T being applied at this end, and then there are two subsequent torques applied along this shaft. We need to figure out what the torque is in between B and C, and in order to do that, we turn to our good old friend equilibrium. Now, when we often perform equilibrium in mechanics with static problems, we usually are first thinking about performing equilibrium on the entire structure. But in this case, we can kind of skip that step because there is essentially, or I gave three torques that all add up or sum up to zero. We're using, in this case, the arrow coming out. This is actually a zero force, but we're using here this as an axis, and then so this T right here is being considered to be a positive torque. But what we have here is that these three torques equal to zero, and so if, for example, I didn't know a torque being applied here or a torque being applied here or even the torque applied here, but I knew the other two, I could use external equilibrium to figure out what the third one is. So we have these torques on this shaft, and we then turn toward what's going on inside the shaft. And let's, in particular, focus on the region between B and C. So if we're drawing this sectioned cylinder, what you see here, this would be C on this side, and then this would be somewhere intermediate between B and C. And it's a good idea to follow the convention that we've laid out for internal slices. And that is that we define a torque to be positive when it's in the direction corresponding to a vector coming out of the face that's been sliced. This is true for axial loads, and it's true for torques as well on shafts. So we're going to call this TBC, meaning it's a torque in between B and C. And there are no additional external forces, or torques, better said, between B and C. So we have a pretty good understanding that it's going to be constant. The internal torque is going to be constant between B and C. On this back end, we have the externally applied torque that was given in the problem. And we know that we can perform equilibrium, and we're going to consider the summation of the torques about the x-axis to be equal to 0. And so we see that TBC is equal to the 2t over 3. Okay, that's what is being applied on this end. And like we said, it's constant. So at this point, what should we do? Well, let's take a moment and take a torque or a moment. Anyway, bad joke. Okay, let's take a look at how a material element might be deforming on the surface of this cylinder or this shaft. And so we've kind of drawn this here, and you can see it is slanted, right? And you could argue, okay, this is not exactly how it looks. It should actually have another slope for these left and right sides. But for now, let's just say I got an idea that there's a torque being applied internally this way, TBC. And so this left side of this, this element is going to be, and maybe I'll zoom in a little bit. This left side of the element is going to be moving a little bit more upward, and this right side of the element is going to be moving a little bit more downward. And so when we zoom in or draw this element, we can say, okay, X is coming out the left side here, right, on this face, and we got this kind of tilted element now. What's causing that tilt? Well, shear stresses, okay? And so we can say, all right, well, this side is being essentially pulled, sheared that direction, this side's being pulled right that direction, and we'll say there's that shear stress causing this, and for this element to be in equilibrium, we've got to have these corresponding shear stresses acting on the top and the bottom portions. So this kind of idea of getting us a deformation or depicting deformation gives us an idea of how the shear stress is actually um, acting on a material element on the surface of the cylinder. What's happening though with the shear stress as we move to different radii within the shaft? Well, here's, let's say, the open face, and let's say that this now uh, edge right here corresponds to this edge over here, and so now we put it on, and we're just, this is being stamped on the exterior of the cylinder. Well, there's a shear stress, right, associated with that face. There's a shear stress, right, tau, associated with this face over here. And there are shear stresses associated with the top and the top and the bottom faces as well. And then what happens on this face of the shaft? Well, we actually have a gradient, and you can look into the notes or textbook, but we've talked about it in the notes that are available, and we also in class. You can see that this shear stress decreases as we get closer to the center line of the shaft. And we call this measurement rho that we take in terms of describing the radial distance from the center. And rho has to be less than the radius of the shaft, which we call c. So as was derived previously, we can say that the shear stress is going to be a function of the radial distance from the center line of the shaft over the polar moment of area, J. We can also say that it's going to max out. That is, the shear stress is going to max out when we get to the outer surface, okay, get to the radius of the object. So we can also write that it's going to be the internal torque TBC times the radius over J. What is J? Again, you can look into the notes, but it is pi over 2 c to the fourth, okay, radius to the fourth. Please note, as we discussed in class, this polar moment of area does not depend on rho, but it completely depends on the geometry of the object, meaning the external radius is what we plug in for this c. The tau max can then be rewritten by substituting 2/3 t into TBC and substituting the j appropriately. So we get that it's 4 times the torque over 3 pi c to the third. So for this problem, whoops, this is the next problem which we're going to do. Let's go ahead and we could do this in Colab, and maybe I should, but I forgot to get it started. So let's just go to Google. I can even type that in. All right, and let's plug in some values. So we've got a diameter of 1 centimeter, and we have a T equal to 85 newtons. So we'll do 4 times the 85, and we'll say, I'm having trouble typing Newton meters. I don't think we need that parentheses, those parentheses, but sure, why not? Times 3 times pi, okay, times c to the third. So what is c? C is the radius. Please note that we have a diameter of 1 centimeter, so this is going to be half of that. And we're going to do it to the third power. And another common mistake is to see, oh, we've got a c, we forget the c. I will do this. I'll forget that there's a c in the numerator, right? And that knocked out one of the c's in the denominator. So let's see what we get. We get, wow, 288.6 million. All right, so we can do this in pascals. So we can put it in megapascals. Okay, so 289 million megapascals. That's not an insignificant amount of stress, especially shear stress. And why I say that will be clear later in the course. Let's go ahead and do the next problem, which is very closely related. I almost made 2 videos, but I thought, nah, just make one. For this problem, we have a similar geometry, exactly the same geometry, in fact, but the diameter is different. It's 1.4 centimeters, and the torque is also different. It's 91 Newton meters, and that's this T here. And what the question is asking is, what is the shear stress at a radial distance, okay, halfway between the center line and the outer surface, right? Again, between points B and C. And it says halfway between points B and C, but as we discussed, the internal torque is not changing as we go from B to C. Okay? But this other halfway is describing the radial distance. So once again, we have a radius of a shaft, all right? And this is the 2D description, obviously. It's looking at the face, it's just a circle. And we have a row that describes that radial distance from the center line. So we're saying it's halfway between the center line and the outer surface. What does that mean? That just means that this distance is going to be the radius divided by 2. And to be careful, I kind of skipped this step formally in the last problem, but this is another mistake that I'll commonly make, being that it gives a diameter, and I'll use it as a radius instead of a diameter. So C is equal to the diameter over 2. And therefore, we plug everything in, and we get essentially a very similar equation to what we got last time, right? In the last problem, we got 4 times the torque times C essentially over 3 pi C to the 4th, right? And those C's canceled out. One of the C's canceled out when this row was a C instead. So now we've got C to the 4th. Let's go ahead and plug in the numbers, and we can go back to Google for that. So we've got, in this case, 91 Newton meters. And we should put a C in, or a rho, sorry, in the numerator. So that's going to be half, okay? So that's going to be times, we got to, okay, so the radius is going to be 0.7 centimeters, and it's half of that, so it's going to be 0.35 centimeters. And I'll go ahead and put it in like that. And the radius is 0.7 centimeters in this case, right? Because diameter is 1.4, and this needs to be raised to the 4th. Okay, so I think that all looks good. If not, let me know in the class. And what do we get? We get about 56 megapascals. Now, we changed the torque and the diameter from the last problem that we were working with. So I don't have, I mean, I would say, oh yeah, well, rho is less than C, so, the amount of shear stress we have is less than what we had last time, but the torque and the diameter changed in this problem. But the statement is still true that if we use a rho that's less than C, which it has to be, we're going to expect that the shear stress that we calculate is less than the shear stress at the outer surface. Well, anyway, thank you for watching, and I hope you found this video helpful for answering these questions.